Good afternoon. So in today's lesson and the next one as well, we will learn two very useful formulas for counting objects. In particular, these formulas are used when you want to number or to count the number of selections you can make from a number of available selections. So for example, questions like, you have 100 people applying for a job. Let's say you have 5 positions to fill in how many ways can you actually select 5 people? Does it matter if they are ordered or not? So notice that there is a nuance here in terms of the ordering. Let's say you want to, let's put it differently. Let's say you want to hire just one person, but out of 100 applicants, you want to select 4 or 5 of them to come for a campus interview, let's say for an academic job. Well, the order matters in that case, maybe because usually you just choose the top 5 ones and then you rank them and then you call them in the order of preference, and then the question is how many arrangements can you make, or in how many ways can you select these 5 people if the ordering matters. Let's say you want to know how many phone numbers you can make, with 6 digits, let's say. So in that case, of course, the ordering matters. But if I ask on the flip side, let's say I have 10 people and I want to form a committee of 4 people, this question suggests that the ordering doesn't matter. So the question is really in how many ways can you choose 4 people out of 10, and you don't really care about the ranking within that selected group of 4 people. So this is a brief overview of these type of questions we're gonna address with these formulas. Once you get the hang of it, these are very useful and also easy to use in many applications. The whole point is to actually set up these formulas correctly. So we're going to start with some preliminary stuff, in particular for those of you who never worked, for instance, with the notation of a factorial, which is used in these formulas. And then we're going to get into the formula itself, one for the permutation in this lesson, and then on the next lesson, the combinations. So before we move on, let me remind you one particular question which we actually solved when we learned the multiplication formula, I think. So if I ask, let's say, in how many ways can we rank 4 candidates for a job? We already solved this question, but remember, this is this is a multiplication formula application. If you imagine you have essentially 4 slots available, right? 1, 2, 3, 4, and then you have 4 candidates to order. You can think in terms of the number of choices for the first position is 4, but the number of choices for the second position is only 3, because once you make a choice for the first position, of course, the number of choices for the second position is 1 less, and then number of choices for the third position is only 2, because you selected already 2 of them, and then you're down to only 1 choice for the last position. So a direct application of the multiplication principle states that the number of rankings for 4 candidates is simply 4 times 3 times 2 times 1. Or since the multiplication is commutative, you could also write it in reverse order, 1 times 2 times 3 times 4, which is actually 24 in this case. I want you to pay attention to this type of expression, which basically is all the natural numbers multiply up to 4. Because we can extend this to a additional quick formula if you want. So we can generalize this and say the number of ways we can rank or order basically n objects is going to be 1 times 2 times 3 all the way up to n, because of the same multiplication principle. Since these types of products appear so often, we're going to make a notation for this type of product, which is called the factorial. So if n is a natural number, n factorial, which is denoted by n followed by the exclamation point, is simply a notation for all the numbers multiplied up to n. 1 times 2 times 3 up to n. 1 is really just to see the pattern here, because obviously if you multiply by 1, that doesn't change the value of the product. But just to reinforce that we multiply all numbers up to n, we write 1, 2, 3 all the way up to n. So this is the n factorial. So we're going to practice a little bit with computing these factorials before we actually get to define the permutation. So the answer to the first question here was basically 1 times 2 times 3 times 4, which is 4 factorial. Like I said, that's 24. If you have another example, for instance, let's say what's 6 factorial, that's 1, 2, 3, 4, 5, and 6 multiplied together. And you can multiply this in any order you want, however you find it convenient. So 6 times 4 is 24, 5 times 6 is 30. You can just combine them however you like. That's 12, 72. So 720. You can use the calculator, of course, if the product gets too large. Now, I want to point out a very important little trick in terms of computing factorials, because often you will see these factorials as numerator and denominators of fractions. And even if you use the calculator, you still have to simplify that fraction before you use the calculator. Otherwise, it takes far too long. So let me illustrate what I'm talking about. So let's say I want to compute the ratio between 50 factorial divided by 48 factorial. And I'm going to actually pull up the calculator here so that I can use it myself. All right, so what you don't want to do, you don't want to multiply all these numbers up to 50 on the top and all these numbers up to 48 on the bottom. Because, I mean, maybe you could do it, but if I put 1000 factorial on the top and, 900 factorial on the bottom, or 980 factorial, that'll still be bad actually. But you still have to simplify this a little bit before you use the calculator. Otherwise, you're going to waste far too much time. What I want you to notice is that when you take the ratio of 2 factorials, so once again, slow down and pause if you need to. You can rewind the video because this is one of the computations you're going to do quite often in these last 3 sections of the chapter. What you have to notice is that the smaller factorial, so I'm going to write it here as a remark. So the smaller factorial is included in the big factorial. When I teach this in the regular classroom, I like to say that you're going to use the principle of the big fish swallows the small fish. So if these are fish, 50 factorial, 48 factorial, the bigger one includes swallowed already the smaller one. So what I mean is that on the top you have all the factors that appear in the smaller factorial. Right? So on the bottom you have 1, 2, 3 up to 48. On the top you have all those factors, but of course on top of 1, 2, 3 up to 48 you also have the following ones up to 50. Right? So the previous factor before 50 was 49, the previous before that was 48, and then from that point on all of these guys represent 48 factorial. So you can think of the numerator as 48 factorial, but multiplied by the additional factors 49 and 50, whereas on the bottom, like I said, is just 48 factorial. So we don't need to write down all the factors like I did here. All you gotta remember is that when you simplify 2 factorials, the smaller one disappears completely, and the bigger one remains only with the additional factors. So I could have said from the beginning, that's what you have to do basically to practice. When you look at two ratios like this, when you simplify, cross out completely the smaller factorial, cross out the bigger one, but complete it with the additional factors that it contains, right? So 48 factorial, and after that follows with 49 and 50. So then it's 49 times 50, and now of course you can use the calculator to figure out what that is, which in my case, that's going to be 2,450. Let's do another example. So let's say I have 73 factorial divided by 69 factorial. Once again, the smaller one disappears completely, and on the top you're left with all the factors that follow after 69. So that's going to be 70, 71, 72, 73. So you see, I mean, even in these cases, you still have sometimes a big computation to do. Let's see, 70 times 71. I think I tapped accidentally the screen, times 72. I don't like to use big numbers anyway, but I just want to make the point. And then times 73. That's going to be 26,122,320. Another important remark which will come very handy later. Let's say you have multiple factorials to pair. So let's say you have 9 factorial on the top divided by 7 factorial times 3 factorial. Now, if you want to make your life easier, because by the way, in this case, you have to, if you simplify, you have to pair either 9 factorial with 7 factorial or 9 factorial with 3 factorial. So as a remark, it's better to pair the bigger factorials close to each other. I'm going to put this in quotation marks because by close to each other, I mean the pairing that gives you the fewest factors. So here's what I'm talking about here. Let's say you decided to simplify 9 factorial with 3 factorial. Okay, then on the top, you're left with 4 times 5 times 6, 7, 8, 9. And on the bottom, you just have to expand and maybe use the calculator to compute 7 factorial. But on the other hand, if from the beginning you decided to combine 7 factorial with 9 factorial, then on the top you're left only with 2 factors, 8 times 9, and on the bottom of course is 1 times 2 times 3. So the second situation is much easier to handle. You still get the same answer, right? I mean, we can actually check this. I'll do that quickly. And you can still do some simplification before you jump with the calculator. That's also useful. So you can divide 9 to 3 and you're left with 3 on the top. 8 over 2, we're left with 4 on the top. So it's 4 times 3, which is 12. So let's see if you go the harder way. Let's do some simplifications. 4, 6, 4, 5, 6, 4, 5, 6, 7 as well. It's not that bad actually in the end. Yeah, I mean, I guess it's not a big difference in this case at least, but in general, remember, so that's of course still 12. Do what I said in the sense that there's kind of a messy here. So that's 12, the answer here. Pair the bigger factorials that are closest to each other. In general, pair them so that you have fewer factors to deal with. One last remark before we finally get into the permutation stuff. By convention, and I'll explain that when we move to the permutation, by convention, we define 0 factorial as being 1. In mathematics, many situations are in such a way that some conventions are made to make our life easier. Because notice 0 factorial doesn't fit the description of the factorial that we talked about, right? All the natural numbers up to n, 1, 2, 3, up to n. So 0 doesn't fit that framework. But 0 factorial appears in some specific formulas, and you will see it's practical to define it to be 1. So by convention, 0 factorial is 1. Keep that in mind as we move along to the second page. So stay tuned. All right, so let's define what we mean by permutations. In general, we're going to say permutations of k objects selected from n distinct objects. So let's illustrate this concept with an example before we give the formula or the definition of those permutations. So suppose I want to find the number of 2-letter codes that can be made or that can be formed using the letters A, B, C, and D, and no repeated letter is allowed. All right, so let's actually do this. Let's do this directly. Let's form these letter codes and then count them. Now notice that when I actually say the letter codes, and the only restriction is that no letter is used more than once, I actually include the possibility of repetition of these letter codes. So I mean, let's actually write down those 4 letters, right? That using the letters A, B, C, D, right? So basically the codes that can be made are A, B, B, A. These are 2 different codes, right? I mean, the problem suggests the order matters actually, right? I mean, if you know already from a password, right? If you write a password or a code, of course the order matters because BA is a different word than AB. And then let's do the other ones. You can have a combination with AC, CA, AD, DA, BC, CB, BD, DB, and finally CD and DC. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Did I do that? Let's see. So 2 letters. 3 times 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes. So 12 possibilities. Right, so 12 letter codes. Now, how do we actually do this in general? How do I actually figure out how to do this? Well, this is basically an application of the multiplication principle. Right, so I mean, if I want to form 2 letter codes, right? So I have 2 slots, and we actually did some problems like this before when we learned the multiplication principle. So for the first code, we have 4 possibilities, 4 letters, and then of course for the second slot we have 3 possibilities. So in total we have 4 times 3, which is 12 in this case. Okay, but how do we extend this to a general formula related to this, right? So I mean, the goal is to basically make a formula involving these number of objects. So what if I have in general n objects, n distinct objects, and we want to select k of them. So by default, k should be less than or equal to n. So n objects, and we want to select k of them. And again, order matters. Right? So in other words, the ordering of the object you select matters. We can use the same multiplication principle for this initial example. So we want to select, like I said, k objects. So let's actually let's do it this way. So object 1, object 2, all the way to object k. And again, k is a number less than n. So for the first object, we have, of course, n possibilities because we have n objects to choose from. When we move on to the second object, we have one less. And pay attention to the pattern here. For the first object, we have n possibilities. For the second object, n minus 2. Let's squeeze in here object 3. We're going to have n minus 2. And so the pattern is that the first object is n, so n minus 0. You can do it like that just to keep the pattern. Second object, n minus 1 choices. Third object, n minus 2. Kth object will be n minus quantity k minus 1. Right? So I mean the stuff that the number you subtract from n is 1 unit less than the slot number if you want, right? Because you select k objects. So the answer to the question of how many ways you can select k objects in which the ordering matters out of n objects is the product n times n minus 1, n minus 2, all the way up to n minus quantity k minus 1. I'm going to keep it like that in parentheses for one particular purpose that you will see immediately. So this is in a nutshell the formula for the permutation. We can define it. We're going to define it in a formal way immediately. But I want to point out that this is the point of factorials. This kind of ugly product, it's much more convenient to be written in terms of factorials. And the way to do it is to basically fill in, think of it as a fraction basically. So this product, think of it as a number divided by 1. You can write the numerator in terms of a factorial by multiplying on the top all the remaining factors up to 1. So I start with n, the previous one is n minus 1, n minus 2, this is n minus quantity k minus 1. After that it follows n minus k, and then you keep on subtracting bigger and bigger coefficients all the way up to 2 and 1. So you basically put on the top and on the bottom all the factors from 1 up to n minus k. Basically, this is like a little proof of the permutation formula. You don't have to memorize how it is obtained. I just want to illustrate it briefly here. So if you want to compare with the example what I had on the top, that 4 times 3 is completed with 2 times 1. And of course, you do the same thing on the bottom, 2 times 1. This allows you to write the top and the bottom in terms of factorials. In particular, what you have here on the top is n factorial, because you have all the factors from 1 to n. And on the bottom, you have all the factors up to n minus k only. And that is just n minus k factorial. So you could think of, for the initial example, you could think of this as 4 factorial divided by 4 minus 2 factorial, which of course is 2 factorial in this case. You don't have to worry about this proof. I just wanted to give you a brief justification if you're interested. All it matters is to remember or use it from the formula sheet, the formula in terms of factorial for the permutation. So now it's time to define, like I said, the permutation in a formal way and to also use a formal notation for the permutation. So the notation for permutation is P of nk, and this represents the number of ordered arrangements. Order is important, right? So order arrangements of k objects, k is less than or equal to n, chosen from n distinct objects and repetition is not allowed. So you cannot choose an object more than once. And the formula that computes the permutations, as we established already, is n factorial divided by n minus k factorial. So let's go over a couple of examples. So suppose, for instance, that I want to choose 8 objects from 10 distinct ones. Then of course the answer is in which ordering matters, right? So choose 8 objects from 10 ones, ordering matters, right? That means you distinguish between different orderings of these 8 objects. So basically the answer is permutation of 10 comma 8, right? So the first number is always the number of objects you select from. The second number is the number of objects you select. So of course that's going to be 10 factorial divided by 10 minus 8 factorial. That's going to be actually a huge number. I should have started with a smaller one, because that's going to be 10 factorial over 2 factorial. And then if you simplify the 2, that's going to be 3, 4, 5, 6, 7, 8, 9, 10. I should have started with a different example. But let's do this one anyway. I'm going to actually do it with, you could do it with Wolfram Alpha. Wolfram Alpha actually knows factorials. You can just enter them in terms of factorials. So 10 factorial divided by 2 factorial. That's going to be, let's see, that's a big number to start with. So it's going to be 814,400. Let's do a smaller one. Let's say I want to do permutation of 6 comma 4. So we choose 4 letters, let's say out of 6. This would be like forming 4 letter codes out of 6 possible letters, right? So let's say you have the letters A, B, C, D, E, and F, and you want to form 4 letter codes. And so that means ordering matters, obviously. So that means that's permutation of 6 comma 4. That's going to be 6 factorial divided by 6 minus 4 factorial. 2 factorial. That means if you simplify the factorial, you're left with 3, 4, 5, 6 on the top. 12 times 30. That's going to be 360. And there are various problems like this. For instance, let's say you have you're a TV scheduling, you're a TV channel and you want to schedule 6 slots. So you want to schedule 6 TV slots, and you have 11 to choose from. Right? So in how many ways can you actually make the schedule, the TV schedule, if you have 6 slots available and you have 11 to choose from? Again, ordering matters. When you talk about the TV schedule, ordering matters. So that's going to be ordered pairs of 6 objects selected from 11. So permutation 11 comma 6. 11 factorial divided by 11 minus 6 factorial. That's 5 factorial. Simplify the factorial, so that's going to be 6, 7, 8, 9, 10 times 11 over 1. I don't want to move to the second page for this. So, and that's why I squeeze it here in this corner. So if you use the calculator, this should be 332,640. So that's how many possibilities are there for scheduling these TV slots. So I think that's it for this section. I would advise you, if you have the time, to move already to the next one, because the combinations are also related to permutations. And so these two sections are better understood together when you actually study them, right? So if you can move on to the next lesson on combinations right away. Otherwise, that's it for now.